All right, so we're in 16.9. This is the last section that we cover in this class, actually. There is a 16.10, but it's not really its own section. It just summarizes several results, and we are going to talk about that at the end of this video, but I'm not even going to be calling that 16.10. I'm just going to consider it like the end of 16.9. Anyways, the topic for this section is the divergence theorem. Sometimes this theorem is referred to as Gauss's theorem, named after Carl Friedrich Gauss, the very, very prolific and famous mathematician who proved lots and lots and lots of different things, but this theorem is among them. So what we're going to do is we're going to walk through kind of like what we've done for Green's theorem and Stokes' theorem. We're gonna walk through an explanation of the statement of the theorem. We're going to prove it, run through some examples, but then at the end of the video, what I'm going to do, or at the end of this section anyways, what I'm going to do is talk about how this theorem actually gives meaning to the divergence operator that we defined back in 16.5. And then I'm going to try and give sort of an intuitive understanding of why the divergence theorem works the way that it does, or kind of explain it in different terms to give it more of like a physical interpretation. So let's just start from the beginning. First of all, when we're talking about the divergence theorem, we're going to use the term simple solid region. Kind of similar to when we proved Green's theorem. In fact, the proof of the divergence theorem is going to feel a lot like the proof of Green's theorem. We need to be working with solids that can be represented simultaneously as type 1, 2, or 3 solids. If you remember back in 15.6 where we talked about triple integrals, we talked about what a type 1, 2, and 3 solid were. Compare that to our proof of Green's theorem where we were kind of proving a special case initially of simple regions that are both type 1 and type 2 at the same time. So here's our statement of the divergence theorem. We're going to let E be a simple solid region, and S is going to be the boundary surface of E, given with positive, which means outward orientation. So remember, if S is the boundary curve of a solid, we call that a closed surface. A closed surface can be something like a sphere or a box, something like that. That's intuitively closed. And we're going to say let F be a vector field whose component functions have continuous partial derivatives. You notice we make that assumption a lot because that opens up some theorems to us on an open region that contains E. Then so this is the surface integral of F across S. Remember, this surface integral, we can call this the flux of F across S. And I'm going to be using that terminology a lot in this section. It's equal to the volume integral, that's the triple integral, over the solid region E that's enclosed by this surface S of the divergence of F. Remember, the divergence will be a scalar field, so this triple integral here makes sense to talk about. So one thing I want to do here is draw a distinction between Stokes' theorem and the divergence theorem, specifically in the types of surfaces that we're talking about. If you notice in Stokes' theorem, we also talk about a flux integral or a surface integral, and we relate it to the line integral along a boundary curve. The difference is that in the divergence theorem, we have to be working with a closed surface, the surface that encloses some solid region. Stokes' theorem doesn't have that requirement. The surface doesn't need to be closed. In fact, if it's not closed, those are exactly the cases where we end up with a boundary curve surrounding the surface somehow, or something that bounds the surface. So we're looking at a very specific type of surface in the case of the divergence theorem. Let's go ahead and get a proof of this in. So what we're going to do is represent the vector field in component form. F is going to be Pi plus Qj plus Rk. And what that means is that if we wanted to actually evaluate the divergence of F, this is by definition the divergence of F. So remember, the goal here is to show that under the assumptions about the solid region E and the boundary surface S, that these two integrals are equal to each other. And just like in the proof of Green's theorem, we're going to try to put each of these integrals into a form that can be shown to be equal to each other. So we work on one side first, and then we work on the other side and try to meet in the middle somehow. I'm going to start by working on the right-hand side. So if the divergence of f gives us this, notice I've turned my integrand here into a sum of three terms, which means I can break it into three separate integrals. Volume integral of partial of p with respect to x, partial of q with respect to y, partial of r with respect to z, all over that solid region E. Okay. Now, if n is the unit outward normal of S, which, remember, when we talk about giving a closed surface a positive orientation, the unit normal is understood to point outwards. So it's pointing away from the solid that the surface is enclosing. But if n is the unit outward normal of S, then the surface integral on the left side, so this guy, let's talk about the surface integral right now, is equal to f dot ds, which, remember, that means f dot n ds, so we dot f with that unit normal, which would be equal to, again, f is pi plus qj plus rk. If I use the distributive property of the dot product, I can distribute this dot n into each one of these to create three separate terms that I use to split this into three separate integrals, three separate surface integrals. So I took the triple integral of my divergence, broke it into three parts. I took the surface integral, or the flux of f across S, that flux integral, broke that into three parts. If I can show that the first part of this is equal to the first part of this, second part is equal to the second part, third part is equal to the third part, then this sum will equal this sum. And that's how we go about proving this, just like what we did with Green's theorem, except we have three instead of two terms to talk about. So that's what these equations are right here. It's equating term by term the pieces that we broke our flux or our surface integral into and our volume or triple integral into. Okay, now also, just like the proof of Green's theorem, proving each one of these independently looks very, very similar. So it's really only worth our time to bother proving one of them, and then we just sort of say, you know, proving the other two follows similar steps. But this is where it's really important that E be a simple solid region, because what we're going to do is prove this equation 4 right here, which is, again, equating the last term here to the last term here. In order to do this, we need to use the fact that E can be represented as a type 1 region. If I wanted to go through and prove equations 2 and 3, I would need to be using the facts that E can also be represented as a type 2 or a type 3 solid. So that's why we had to make that assumption that E is a simple solid region at the beginning of this. But for this equation right here, to prove that equation 4 is true, we use the fact that E can be represented as a type 1 region, which, remember, by definition, this is what a type 1 region is. X and Y belong to some plane region, and Z is bounded by functions of X and Y. That means that this U1 of XY is going to represent a bottom surface for our closed surface, and or a bottom part of that surface. U2 is going to represent the top part of that surface. I have a picture on the next page that I'll show you to point that out again. So when we talked about evaluating triple integrals of type 1 regions back in 15.6, we said that if you want to find the triple integral, and remember, this is the triple integral that we're talking about. Triple integral of the partial of r with respect to z dv. So I want to work on this guy right now. Using my representation of E as a type 1 region, I can write this as the, or let me start here, the double integral over the plane region D that's described here of the definite integral from U1 to U2, these two functions of X and Y up here, of the partial of R with respect to Z, of the partial of R with respect to Z dz, okay? Now, notice there's a derivative with respect to z here, and I'm integrating with respect to z here. This is where we use the fundamental theorem of calculus to basically say that this integral, the antiderivative, is just r. evaluated using these limits of integration. So if I do that, if I evaluate this integral and get r evaluated at these limits of integration, then I get this as my integrand on the double integral over d here. So r of xy u2 minus r of xy u1. That would be the result of this definite integral in here. Okay. So that gives us a representation for the triple integral that's on the right-hand side of this equation here. All right, let's go ahead and move on to the next page. So here's an image of the solid, or possible solid, that we described as our type 1 solid, E. You notice E has a top surface and a bottom surface given by those functions u1 and u2. I'm going to name the bottom surface S1 so that I can reference it in a surface integral. Top surface, I'm going to call that S2. And then the surface that sort of wraps around the side, that entire thing we're going to be calling S3. So really my type 1 solid here has a boundary surface that can be thought of in 3 parts: S1, S2, the bottom and top, and then S3, the wrap around the side. Okay. Now, a few things worth noting here, or actually kind of just one really important thing, which is mentioned in this little paragraph here. This surface, remember, this is meant to just be some kind of general type 1 surface, but type 1 surfaces have lots of different shapes, and in some cases, S3 doesn't even exist. In the case of a sphere, for example, this vertical surface that wraps around the side shrinks down to basically a curve or a point. So it's possible that S3 is not even a vertical surface at all. It's just the top surface meets the bottom surface. But that's going to end up not mattering, it turns out. So what we're going to do is take the surface integral. Remember, whoops, wrong side. What we have done so far in this equation is we've come up with a representation for this triple integral, which is here. Okay. Now what we need to do is take this surface integral and kind of mess with it, put it in a different form, and see if we can match it to what we got here, which would establish that these two things are equal to each other. So that's where we're working now. I want to talk about the surface integral over S of rk dot n ds. But S, which is the entire boundary surface, we're going to break into those 3 parts, S1, S2, and S3. So really, I'm going to look at each of those parts independently. Starting with S3. Because, again, this is a type 1 region, this is where, or type 1 solid, this is where that's really important. The surface S3, that surface on the outside, its outward unit normals are going to be horizontal. They're going to be pointing outwards, and they're going to have 0 for their k component. They're all going to be pointing horizontally. We're dotting that unit normal n with k, which is a vertical vector. What that means is that k is orthogonal to n anywhere we're looking at that outward unit normal. But that would mean that their dot product is 0. Well, I'm pointing to the wrong one. I should be pointing to this one. So k dot n is equal to 0, which means my integrand is going to become 0, which means the integral itself is going to equal 0. So when we break our surface S into those 3 parts, and then take the surface integral over each of those parts, the surface integral of S3 just goes to 0, goes away. Meaning the only 2 surface integrals that actually contribute anything are the ones over S1 and S2. So the bottom and the top. So that's what this is saying here. The flux, or the surface integral over S of rk dot n ds can be just thought of as a sum of 2 surface integrals over S1 and over S2. All right. Now, here's where we use our representation of our solid region E to be a little bit more specific about the surfaces S1 and S2. Remember, S2, our top region, is the graph of a function, z equals u2 of xy, where xy belongs to this plane region D. Remember, D is the projection of this solid into the xy plane. So in this first case, remember the outward unit normal n is going to be pointing upwards because this is the top surface. If that's the case, if it's pointing upwards, then k, which also points upwards, is a dot product of two vectors that are pointing in the same direction. That's going to mean that the dot product is just equal to the product of the magnitudes of these two vectors, both of which are equal to 1. So this dot product, k dot n, is just 1, which means I'm looking at the surface integral of, my surface integral is going to become the double integral over d. Remember, this is how we evaluate these surface integrals, of r of xy u2. I make substitutions for the surface up here. Okay. Now, what about on S1? Well, if we're talking about S1, remember the outward unit normal n is going to be pointing downward, because that would be out. That would be pointing outside of that solid region E. So if I have k dot n there, remember k is pointing in the exact opposite direction. K is an upward unit vector. So that means that the dot product, these two vectors have a 180-degree angle between them. The dot product here is going to be equal to the product of their magnitudes times -1. So, sorry, I should be pointing at this one. So k dot n in this case is equal to -1. That -1 is brought out, and I end up with a double integral of d over d of r of xy u1 xy. So back up here where we said that the surface integral over S is the sum of these two surface integrals, one over the top surface, one over the bottom surface. Using the fact that the bottom surface gave us a negative, the sum of these two things actually looks like this when we combine them into a single double integral. That sounds weird when I say that, a single double integral, just a double integral. Notice that this is exactly what we had here for the volume integral, or the triple integral that we did previously. So that establishes the equality that we wanted to show. Again, similar method, or a similar method can be used to prove the equality of these other two equations, which would finish the theorem off, but not worth our time to go through all those steps again. Okay, so that proves the divergence theorem. What I want to do is use it to show you how effective it is at evaluating or determining flux of a vector field over a closed surface. So here's our first example. We're given a vector field f of x, y, z, and this is it, x squared y z I plus xy squared zj plus xy z squared k. And the box S is defined to be the surface enclosing, or sorry, let me say the boundary S of the box S. I realize I worded this kind of weird. So I should be calling the box E probably. S is going to be the surface of the box. That's the way I should be saying that. So S is the surface of the box enclosed by the planes x equals 0, x equals 1, y equals 0, y equals 2, z equals 0, z equals 3. Our goal here is to find the flux of F across S, which is the same thing as finding the surface integral over S of F dot ds. So let's start by sketching this box, just to see what we're working with here. X is equal to 1, y is equal to 2, z is equal to 3. The box enclosed by these planes, you can see, would look like this. It's this guy right here. Okay. So the solid region representing the entire box, I'm going to call that E. And boxes are the easiest things to work with because this box E as a set is just this. The interval 0, 1, 0, 2, 0, 3. It's the Cartesian product of these three intervals. Remember, this turns into the limits of integration on my triple integral that I'm going to do. So what we're looking for is the flux of this vector field across the boundary of this box, across the surface. surrounding this box. The divergence theorem gives us a method for doing that. I could calculate the surface integral of f dot ds by itself. That would be really, really complicated because this surface is made up of 6 surfaces in total. That means I would have to do 6 different surface integrals. One surface integral by itself oftentimes is complicated enough. Having to do 6 of them and then sum the results is not my idea of a good time. So what I'm going to do is use the divergence theorem and say that this surface integral can be alternatively evaluated as the triple integral over the box E of the divergence of f. So really the first thing I need is to find what the divergence of f is. Divergence of f. So looking at how I defined f up here, partial with respect to x would be 2xyz plus the partial of the j component with respect to y would be 2xyz again, and then notice 2xyz here as well when I take the partial with respect to z. So that gives me 6xyz for my divergence. Well, using the divergence theorem, what this means is that the flux f dot ds is equal to the triple integral over E of the divergence of f dv, but the divergence of f is equal to 6xyz, and this triple integral right here is our favorite type because I don't need to think of it as type 1, 2, or 3. I actually just get to use the simplest case of constant limits of integration here. 6xyz dz dy dx. It's perfect. Okay, I'm going to bring the 6 out, and because I have a product of x, y, and z, I can split this into the product of 3 separate integrals. So this would be 6 times the integral from 0 to 1 of x dx times the integral from 0 to 2 of y dy times the integral from 0 to 3 of z dz. Now if you evaluate these integrals independently, I'm going to get 6 times, this would be 1/2. This one comes out to 2. This one comes out to, it's 9 over 2, so it's 9/2. Okay, we get some cancellation here. That becomes a 3. I end up with 27. Okay, notice that did not take much time in the grand scheme of things. That was actually one of the easier problems we've seen in this entire chapter. It would have been awful to do by just evaluating this surface integral directly, because again, 6 different surfaces I have to break this into in order to make that work. Granted, if you know what you're doing, some of those surfaces may not be all that difficult, but it's still much, much easier to use the divergence theorem here. So I'm going to wrap this video up here. We'll do another example, a couple more examples in the next video, and kind of wrap things up there.